It's just audio.
Okay. All right, good afternoon and welcome to the webinar on algebra from numbers to graphs to symbolism. I'm Maria DeLucia and I'm here with Frank Gardella from Hunter College, and we will be presenting this afternoon. So as I've stated before, if you have any questions or comments, there is the chat. If you if you type in the chat, we will be glad to answer questions, so do not hesitate to ask questions as we're going along. So if you have any comments or things that you would like to state, please feel free to type in the chat. Okay, so let's get started this afternoon. Oh, okay. Okay, so our objective this afternoon is to talk a little bit about the algebraic structure, critical thinking, problem solving, and decision making. And as all roads lead to algebra, when you are doing your middle school math, they lead to algebra, and your calculus and your trig and your advanced math all come back to algebra. Algebra seems to be the center of doing math and how it leads to advanced math and how we develop our critical thinking skills from the middle school. So as I say, all roads lead to algebra. That's what I tell my students. Okay, where do we use algebra? And this is the biggest question, especially when you're dealing with middle school children. Where do we use it? So I tell them we're looking to save money to buy a PlayStation, a scooter, a bike, whatever. Cooking, increasing or decreasing a recipe, paint a room, how much paint to buy, what's the cost. So these are things that students need to see. Taking a trip, the cost of gas today. How long will the trip take? So these are questions, and I tell students that whether we use algebra formally or informally, we are using algebra every day. Those are the critical thinking and problem solving skills that we develop when we're looking at algebra. So these are the skills of how to do an analysis, how do we set up a problem, how do we solve that problem, how do we look at different situations and come up with a solution. So this is what we're looking at. Okay, and of course the mathematical practices, which we are supposed to be developing our problems based upon. Making sense of the problem and persevering to solve them. Reason abstractly and quantitatively, that's important in algebra. How do I reason abstractly? Students can do things sometimes numerically, but now when we start to use them in going into the unknown, the abstractions using letters, it starts to become a problem. They cannot see that, they cannot make that transition. Construct a viable argument and critique reasoning to others. That's an important part of when I solve a problem today. Can I validate my answer by talking about how I did the steps, being able to explain the reasoning, modeling the mathematics, whether it's drawing pictures using manipulatives, how do I model that mathematics? Using the appropriate tools strategically, how do I develop the tools that I need? Attending to precision, and that sometimes becomes a problem. Students look at an answer and don't logically look that that answer cannot make sense, the precision. Looking for and making use of structure. How do I do these problems? That's the algebraic structure. How do I solve an equation? How do I solve a word problem? What's the structure that I use? And looking for and expressing regularity in repeated reasoning. So how do I reason through a problem? Okay, an important part and what's become a big thing today with the Common Core is talking about the habits of mind. How do I get students to make this second nature, the habits? So, excuse me, it's looking at the standards and looking at these standards, and if we demonstrate problems and get them to do these problems, these habits of mind, these standards become just second nature. It's looking at this making sense of the problem, reasoning abstractly, constructing the arguments, modeling, using the tools, looking for structure. So it's looking at all of these standards and all of these practices and getting them to just become second nature. So if we look at dissecting these habits of mind, practices, and the standards, overreaching, the overarching, is being able to make sense of the problems and persevere in solving them and attending to precision. You want to make sure you have an accurate, reasonable answer. But when you're developing problems today and you're looking at tasks, how do I look at these tasks for habits of the mind? So if I want to reason and explain, I want to make sure that my task or my problem reason abstractly and quantitatively, construct viable arguments, and critique the reasoning of others. So again, those are the two standards if I'm asking them to reason through a problem and explain, to demonstrate. Modeling, using models, manipulatives to demonstrate an answer. So you're going to model with mathematics, and what are the tools that I need to come to that answer? And then looking at the structure and generalization. So making sense of what I'm doing. Am I using the correct algebraic properties? Looking for and seeing if there is a repeat in the reasoning. Is there a pattern to what I'm doing? So today, I know there's a lot of concern about teaching to the test. Well, if we develop our problems using these standards and these habits of mind, I don't think that we would be teaching to a test. We are now developing problems and tasks that are a little bit different from what students are normally used to. Maybe not what's in the textbook today, but looking at being able to explain, looking at using models and manipulatives, and can I explain? Is there a pattern to what I'm doing? Does it seem that if it works for one problem, does it work for every problem? A contradiction if it doesn't. So these are looking at the habits of mind, becoming the second nature. So again, here is a grid of stating that if I want my students to be mathematically proficient, here is how I'm going to look at making sense of a problem. Critique and reasoning, and these are the steps or the ways of being able to address this or assess this. So being able to explain the problem to myself. So when a student reads a problem, do I understand the problem? Do I understand what the words are telling me? What's the information that's been given? We know that it's very hard for a student who will say, I don't understand the problem. Well, let's dissect the problem. What have I been given? Let's reason through the problem. You know, do I understand what assumptions I need to make? How do I analyze it? How do I break it down? Perseverance in solving these problems. You know, do I persevere in solving them? You know, sometimes a student, and it's a big problem, they read a problem once, say, I cannot do this problem. I don't understand it. So they don't persevere. So problem. So, and the important part is being able to empower the students. How do I empower them to be able to solve the problems without getting frustrated? You know, making sure that they understand the tools, modeling with the mathematics. I think using manipulatives today or any tool that will help them understand the mathematics and be able to apply it is important. And then the important part of being able to reason abstractly. Going from numbers to letters, that's that big abstraction that they have a problem with. So how do I do this? How do I change things into symbolism? I tell my students we're going from the English language, the verbal, to the mathematical language of the symbols. How do I change it to the symbolism? And then again, looking for patterns in the problem, looking for how I'm going to solve this. What are the methods? And, you know, as students will say, well, you've done it the long way. Is there a shortcut? Well, sometimes there is a shortcut, sometimes there isn't. But they have to understand the underlying principles before they can go to a shortcut. And then making use of the structure, making use of the problem, analyzing it. Does my answer make sense? Does my answer make sense? You know, having a student tell you, oh, I'm going to pay $600 for a bike when that's not what it's going to cost, or I'm going to take $600 to fill up my gas tank. Does it make sense? They have to have the reasonability of what an answer should be. Okay. Based on our traditional standards and the Common Core, what are the shifts that we have? The shift in being able to look at the algebra today. Well, it's algebraic expressions are being treated both from a formal and a functional perspective. Functions have become a big part of Algebra 1. Looking at these functions, not just linear functions, but exponential functions, quadratic functions, not maybe being to solve an exponential function or to solve a quadratic function, but looking at graphs to be able to look that we do not live in a linear world, that there are different types of relationships and different types of graphs. Algebra is connected to but distinguished from functions, that we have expressions and we have equations and we have functions, because not every relationship is a function, so being able to look at that. Building equations, expressions, and functions, being able to build them, to create a function, to create an expression, create an equation. And the biggest emphasis throughout is modeling. How do we model all of this? Algebra today, when I teach Algebra 1, I tell students that that's not an equation, that's a mathematical model expressing a relationship between two quantities. That equation is a mathematical model. So I get them into understanding that I'm talking about a relationship between two quantities, and this represents this model. Okay. The areas of concerns that we have in algebra today. Students have trouble expressing generalities with algebraic notation. Well, how do I go from the specific to the general? How do I go from these numbers to this general? You know, algebra is a generalization of arithmetic. Sometimes we hear as a rule. Well, how do I make that generalization? Getting them to understand that the structure of arithmetic holds with our structure of algebra. That structure, again, going back to the algebraic structure, is just building upon our structure from our numeracy. This is especially prevalent when they have to set up equations and solve word problems. You know, how do I develop this? How do I create these word problems? Sometimes students can go through and mimic what we do in solving an equation or factoring or multiplying two algebraic expressions, but when it comes to putting that all together and solving word problems, that's where the problem or the difficulty arises. One of the biggest problems the students have is many students have the difficulty with slope, graphing lines, and finding equations of lines. Teaching a calculus class, and in calculus we have to find the equation of a line tangent to the curve. They've seen finding the equation of a line in Algebra 1, Algebra 2, pre-calculus, and they get to calculus, they still cannot find that equation of a line. When I ask them what they need to find the equation of a line, they look at me and I say, what two important things do we need? We need either 2 points or we need a point and a slope. Given 2 points, I can find the slope. Now I have a point and a slope. I can find that equation. And it just seems like it goes way above them to find the slope. And what is the slope? What does slope mean? They always tell me rise over run. Yes, it's rise over run, but what really does it mean? It means a change in the vertical over the change in the horizontal. It's a ratio of change. Here again, building and using algebraic functions is another place where students are struggling. And in the Common Core today, when they start talking about functions and these relationships, this is becoming another area of concern. How do I get students over this hump? Okay. Dick Lesh came up with a model. This model is stating that when you're trying to do mathematics, whatever form of mathematics, we go from the written symbols, from the spoken language to the written symbols, pictures, manipulatives, relevant solutions. It's all intertwined. They go from one to the other. This is all, no matter what type of math you're doing, what level of mathematics, this is intertwined. It's this ability to go from one form to another, from the written word to the mathematical symbolism, to the mathematical language, and how I solve that problem, drawing pictures, using manipulatives, making sure that my solutions are relevant, they make sense. And I think that's an important part of getting the students to understand. You have to make sense of your solution.
So what we've done is we've created this M4 model. And really, in a sense, our thinking is that if you want students to use modeling as a tool for problem solving, you have to, in a sense, teach them how to model right from the beginning when they're ready. There's no sense in teaching symbolism and then trying to teach them the model. It's like telling somebody, you can drive a car, do you want to know how it works? No. Once I can drive the car, most people are not interested in how it works. And that's the same thing with kids. Once you've shown them something symbolically and then try to go back and say, well, let's really investigate how this is done, there's a resistance on their part because they're still consumers as opposed to people who want to do analysis. So the first part of our model is this kinesthetic, in which basically no writing is used. It is all about the models. Whatever model you're using, algebra tiles, fraction tiles, no matter the model, it is kinesthetic. The language used is oral language. So the oral language and the models form the basis for the instruction. The next level is the language model, and this connects the kinesthetic to common language, social language, basically. There's not too much vocabulary here because the students are still trying to understand what's going on. And all vocabulary, when you add vocabulary in at this time, all it does is create confusion because they're still trying to internalize what's going on with the modeling. Finally, the third step is the fact that we want to take that kinesthetic and that language idea and connect it to the symbolism. So what we do is we continue to use the models, we continue to use the language, and then we start to show them how the symbolism is another way of communicating or expressing the mathematics, and in this case, the algebra. And finally, the last step, obviously, that we want them to get to is the symbolic. However, in arriving at the symbolic, what we have also given them is a basis from which they can draw if, in fact, they become confused or if the symbolism doesn't make sense to them. They themselves then can go back and think about what they did at the kinesthetic level, at the language level, at the connecting level, and in a sense redevelop the symbolic level. That's our goal with the M4 model.
Okay, I'm going to ask you, here's a task. Here's a task, and I want everybody to choose a number from between 2 and 6, a whole number from between 2 and 6. Okay, so I want you to write down a number between 2 and 6. Then I want you to double that number. That means to multiply it by 2. Okay. Take your answer in B and add 3 to it. Take your answer in C and multiply it by 2. Then take your answer in D and subtract 6. Now take your answer and divide it by 4. And what did you get? Should have gotten basically the number you started with. So here is a mathematical number puzzle, and it starts to talk about the structure. I'm multiplying, I'm adding, I'm dividing, then I am undoing. So I'm creating and undoing. So here we can work with these puzzles. You can use it for 2, 3, 4, 5, 6. I mean, we kind of limited it here. You can use it for any. There are many of these puzzles. So now I have this puzzle. Why does it work? How come? So now let's look at the symbolic representation. So I'm going from giving you words to let's talk about what is the symbolic representation here. So I'm going to let n equal the number. The next step stated, take that number and multiply by 2 times the number. So that's 2n. Then it's telling me to take that number and add 3. So now I have 2n plus 3. Part D is where a lot of students have a problem in writing this next step. It states 2 times, as I stated in the problem before, it was take the number that you got in C and multiply by 2. So the number I got in C was 2n plus 3. Multiply that by 2. Some students write it as 4n plus 3. Some students just write it as 2 times 2n plus 3. It's the quantity. So how do I get them to understand that 2n plus 3 is my number? It represents a number. Then it's now stating take the number that I got in D and subtract 6. So it's 2 times the quantity 2n plus 3 minus 6. In simplifying it, because if you want to show students that I'm doing something and then I'm undoing it and how I will get back to n, students will take that number and rewrite it as 4n plus 6 minus 12. They're not realizing that I am only multiplying the quantity 2n plus 3 by 2. So as they learn eventually that this is the distributive property, and I'm taking my distributive property and I'm just multiplying everything that I have there by 2. If I simplify that, if I go through the algebraic structure, that will end up with I have 4n. But if I go to the next step, it states take the number that I had gotten in E and divide by 4. So the structure there is 2 times the quantity 2n plus 3 minus 6, that whole quantity divided by 4. So then if you simplify it, you're going to get back to n. So there is the mathematical structure going from the word problem, a simple word problem, a number puzzle, to the mathematical structure of symbolism, and going through some algebraic manipulation of my expressions here. This is not an equation, this is an expression, and how I can simplify it to show them that I created some number by doing an algebraic or an arithmetic operation, and I did it by adding, I subtracted, multiplying, I divided, inverse operations, and I get back to my number. An activity for the students to do would be to create one of these puzzles, to create one. So let's go.
So what we're going to do now is let's go back to point D there for a second. We all know all the best wrong answers that our students give us about multiplying 2 times the quantity 2n plus 3. And let's look at how we develop the distributive property. And what we're going to do here is we're going to start basically at first steps, which is where we're going to model what we want them to do.
Okay. So here is a video, because the distributive property is a very important property in solving equations, factoring, multiplying polynomials, so therefore we need to develop this concept on a solid footing. So here is how we're going to do this. Oh, I have to go back one, and I'm sorry. This is I must have done something on the back one. Okay.
There we are.
Here we are.
Let's look at an algebraic expression using materials. So the bricks will look like this. We're going to have 4 A's, and we're going to have 3 1s. So this is 4A and 3. The question we want to answer is, what happens if we have more sets of 4A and 3? What do we get as a total? Well, let's put another set of 4A and 3 here and see what happens. So there's another set of 4A and 3. So we have one set of 4A and 3 and another set of 4A and 3. And we can deal with it that way. We can say we have 2 sets of 4A and 3. Or putting all the A's together and by putting all the 1's together. So now instead of having 2 sets of 4 A's and 3, we'll have 1, 2, 3, 4, 5, 6, 7, 8 A's and 1, 2, 3, 4, 5, 6, 6 1's. So we could either have 2 sets of 4 A's and 3, or we can have 8 A's and 6 1's. And I think you see there that we start with basically taking the basic idea of what multiplication is and applying it to an algebraic expression. So what we had was we had 4a plus 3 times 2. We know it that way. But we started with what is multiplication all about? It's taking multiple sets of something. And that something sometimes we can call a quantitative noun, and the number of sets we take is called a quantitative adjective. So in this case, the 4a plus 3 was the quantitative noun, and we have 2 of them, which is the 2 becomes the quantitative adjective. Where we go from here is we start to talk about how we record this. The work is still happening with the materials. It's still happening with the models. The question is, how do we move the students from using the models to some kind of recording device, which will eventually lead to the symbolism. So here's another video which shows how this can work in terms of moving from just the models to a recording device using words.
Because if we go back to our number puzzle, in step step D, it was 2 times the quantity, 2 times the 2 times my number plus 3. So it would be 2 times the quantity, 2n plus 3. If a student didn't realize what that meant or how to solve that, they would have never gotten to the final step of n. So using the distributive property right in that step is an important piece on how I'll get to my final answer of taking that I started with a number and I got back to that number. So that's an important property there.
And one other point is that what we've found with modeling is that the arbitrariness, if I can call it that, of mathematics that some students see it as disappears. Because if I have 2 sets of 4 A's and 3, I can't get anything else other than 8A and 6. There's no other way. So because if people just introduced the distributive property as, we call it, the arrow shooting, as you know from textbooks, the kids wonder, well, can I do it some other way? The modeling shows that it cannot be. Now the real deal here is how to show them that that modeling can be recorded mathematically. Let's look at the expression 4a and 3. And let's record that. So we have 4a plus 3. And what we want to do is we want to look at what happens if we have more than one set of 4a plus 3. So let's look at another set of 4a plus 3. So now we have 2 sets of 4a plus 3. And the question is, how much do we have? Well, we can always say that we have 2 sets of 4a plus 3. We have one here and one here. Or we can look at this as a total. So let's look at what happens when we take our 2 sets of 4a plus 3 and put them all together. What's going to happen? We put all the A's together, and we put all the 1's together. When we put all the A's together, we get 1, 2, 3, 4, 5, 6, 7, 8 A's. So we're going to say that 2 sets of 4A gives us 8A. When we put the 1's together, we're going to get 1, 2, 3, 4, 5, 6. So we say that 2 sets of 3 is going to give us 6. So therefore, 2 sets of 4a plus 3 is the same as 8a plus 6. It's just rearranged differently. In the first case, we were looking at each set separately, and we were looking at 2 sets. In this case, we were looking at totals. This is the total of what we get with a's and numbers when we have 2 sets of 4a plus 6. We have 2 sets of 4a, which gives us 8a. We have 2 sets of 3, which give us 6. So 2 sets of 4a plus 3 gives us 8a plus 6. And now we're going to look at what happens when we move that from the symbolism. And what I'd like you to do is listen to the words, listen to what is said, because it's the oral language that starts with the kinesthetic and is brought through to the symbolic that makes the link between the modeling and the way we express it algebraically. Let's look at the expression 4a plus 3. So in this set, I have 4 a's and 3 1's. But suppose I have 2 sets of 4a plus 3. That means I'm doubling 4a plus 3. That means instead of having just 1 set of 4a plus 3, I'm going to have 2 sets of 4a plus 3. That means I'm going to have 2 sets of 4a, and that's going to give me 8a. And I'm going to have 2 sets of 3, and that is going to give me 6. So when I have 4a plus 3, and I want to look at 2 sets of them, I can do one of 2 things. I can write it as 2 times the quantity 4a plus 3. That means I have 2 sets of 4a plus 3. Or I can look at the a's all together. So I have 2 sets of 4a's, which gives me 8a. And look at the 1's together. I have 2 sets of 3, which gives me 6. And this is the way we work with a multiplication of a number times a quantity. And this is called the distributive property of multiplication over addition.
So here's a task which is a little bit more advanced than what we were just doing. Consider the algebraic expressions below. N plus 2 quantity squared minus 4 and n squared plus 4n. Find some algebraic way to verify that the 2 quantities are the same. So now I'm expanding it, and I have to understand that n plus 2 quantity squared means n plus 2 times n plus 2. So I'm expanding my distributive property not to be just a monomial times a binomial, but 2 binomials. So how do I do this? Let's talk about a way excuse me, of looking at how to verify this. How would they verify it? Some students square everything. So they would square the 4 and say, well, I'm squaring the first term. It means I have to square the second term and I'll get a 16, and then they do not come out with the correct answer. You know, they're not looking at the structure here. So these are common errors. So looking at this. So let's look at this and let's take a moment to say, how would I verify this? How would I verify this? So basically, it's taking my n plus 2 quantity squared and rewriting that as n squared plus 4n plus 4 minus 4. The 4's will subtract out, and I get my n squared plus 4n. The 2 expressions are equal. So again, it's taking something, and if they have a basis or a fundamental concept of the understanding of what I mean by distributive property, how do I expand it here to something more that I'm taking n plus 2 times n plus 2. Everything in the first quantity is multiplied by everything in the second quantity. But I'm talking about the quantity not the minus 4. Let's revisit our number puzzle. Let's revisit it. So again, for each number in the range, each integer, each whole number between 2 and 6, we will call this the number. We will now use the number to do just steps B, C, and D in the puzzle. And the answer that we get in D will be called our total. So I want you to do the number puzzle and figure out what the total would be for 2, 3, 4, 5, and 6. So let's take a moment and look at coming up with a table, N being our number and T being our total, N being the number and T being our total. So we're going to create a table of values.
And again, the number puzzle is you're going to take the number, you're going to double it, add 3, and then double it. And as soon as you double it that second time, that's going to be your total. So for example, if you took 2, you would double it and get 4, add 3 and get 7, and then double it again and get 14. That's what goes in the total column.
So basically, this is what you are creating, a table of values. The numbers 2, 3, 4, 5, 6, and the total after step D. So you're creating a table, numerical table. So after we've done that, this is what the table should look like. We have the number 2, the total would be 8. The number 3, the total would be 12. The number 4, 16. 5 is 20. 6 is 24. So I'm going to call this now my set of ordered pairs. So when I put in a 2, I come out with a total of 8. When I put in a 3, my input is a 3. My output is a 12. So I'm looking at creating a table and a set of ordered pairs. So here are my ordered pairs. Here are my ordered pairs. Now I'm going to ask the students to graph these ordered pairs, to graph them. My input, my number is on the horizontal. My output is the vertical, so I would graph the value of 2, 8, 3, 12, 4, 16, 5, 20, 6, 24. So if I graph that, this is what I'm going to get. Here's my graph of my ordered pairs. Okay. So what do I notice about this graph? I notice that this graph is linear. Everything seems to be increasing at a constant rate. Well, if I go back to my table, do I notice anything about my table? Ask the students to notice, do I notice anything about the table? In this, I have not used the word slope. I have not used the word rate of change. I'm asking you, do I notice a pattern? Do I notice a pattern in my table? Do I notice a pattern in my graph? Do I notice a pattern in my graph? Looking at this. So again, looking at repeated structure, looking at, when I look at my Common Core, my standards, my mathematical practices, looking for that structure, looking for the repeated process. Do I see a pattern to this? So I'm looking at this. Do I see anything that could possibly represent a rate of change? If I notice that for every 1 unit of increase as I went from 2 to 3, or from 3 to 4, or from 5 to 6, my numbers increased by 4. My numbers increased by 4. So every 1 unit of increase in my number, as I increased my numbers by 1, my totals increased by 4. So I'm looking at a rate of change. As the numbers increased by 1, my totals increased by 4. So there is a rate of change. When we did the the webinar on ratio and proportion, I can say that this is a 4-to-1 ratio. 4 units of increase to 1 unit of increase. So this is a ratio. It is a rate of change. So I'm getting students to look at what is a rate of change here, that things are increasing at a constant rate. I have not used the word slope yet, but this is what you're looking at. So if you look at, here is a graph where I've plotted points, and I look at ratios of change. Any point that lies on that line has to have the same ratio, same rate of change. So I have a 5/4 line where my ratio could be greater than 1. I have 3 to 4. For every 3 units of change vertically, there's 4 units of change horizontally. For every 2 units of change horizontally, there's 1 unit of change vertically, depending upon how you want to talk about it. So here are my points, and I notice that if I plot these points and I connect these lines, here are the lines of a ratio of 1 to 2, 3 to 4, 5 to 4, 1 to 3, looking at a ratio of change. My previous problem, I was looking at a ratio of 4 to 1. For every 1 increase in my input number, my output increased by 4. So you're looking at a rate of change. So here again, I could be looking at these rates of change, looking at percentages, looking at what it actually means in a different light. So again, it's looking at, and again, being able to interpret a graph, looking at and analyzing what is my data telling me, what is my information giving me. So I'm looking at analyzing, answering questions, being able to answer questions, explain, and another important part, being able to explain to another. When we looked at the habits of mind and looking at the structure of the problems and creating problems, can I explain to someone else, to communicate to someone else? And that communication skill is not new to the Common Core. That communication concept came with the principles from NCTM. When you looked at the principles, that was one of the principles, being able to communicate the mathematics. So that's not a new concept. So what does this actually mean if I looked at a problem? Here would be a problem that you can give to students. Again, it's a ratio problem. For every 5 cups of juice, you're going to mix 2 cups of peach juice. So the ratio would be 5 to 2. So I'm talking about X cups of grape to Y cups of peach. So here is my, when I have 0, 0, 5 to 2. If I divide the 5 by 5, I'm going to get 1. So I divide both, I get 2/5. So here is my table of values. Here is my table of values. So if I graph this, here is my graph showing that I have this constant rate of change. Constant rate of change. So if I now ask for a relationship to my my peach juice to my grape juice, here is my relationship. If you look at creating this table, as I go from 1 to 2, it means I'm multiplying by 2. When I multiply by, and if I increase by 3, it's 3 times 2/5. So if you look at this, everything is increasing at a constant rate of 2/5. How can I create a relationship? So I can create this relationship that's saying that the number of cups of peach juice is equal to 2/5 times X, where X is the number of grape juice, cups of grape juice. So you're looking at this as I'm going, here is my line, showing that I have this constant rate of change. This is an application. Again, I'm going from a table to a graph, and I'm asking you to explain, to develop this mathematical model. This is a relationship. You're talking about developing a relationship, because if I have 1 cup of grape juice, 4 cups, what if I have 10? What if I have 20? What is the relationship? So X would be the number, and here is my relationship. Okay, so here would be a problem. Here's the problem. Y is equal to 3x minus 2. Do the points on the line a constant ratio? What did I type here? Oh, I must have been really sick when I typed this one. Of a constant ratio of the y coordinate to the x coordinate. Explain your answer. So again, we're getting them into, not only could I graph this, can I look at the lines? Could I explain the answer? Can I explain? Can I explain to someone what, in mathematical terms, what I am doing here? Can I explain in mathematical terms what I'm doing? Okay. All right. Creating an equation from a word problem. That happens to be one of the most horrendous things that students think we can do to them. Why did we develop algebra? Why do I need this? Well, here's a problem. A checking account is set up with an initial balance of $4,800. $400 is removed from the account each month for rent, and no other transactions occur on the account. So I'm constantly drawing $400. Write an equation whose solution is the number of months it takes for the account balance to reach 2,000. So you're asking them to take the verbal into the mathematics, into the mathematical symbolism. So I want to come up with an equation. I'm starting out with $4,800. Each month you are taking out $400 for the rent. You're not adding anything to the checking account. It's just there, and $400 comes out every month. And I want to know how long it's going to take to reach 2,000. So here's how we, since the account starts with $4,800 and is decreased by $400 a month, then what I'm saying is that $4,800, my 400, because the first month I'm going to take out $400. The second month it would have been $800 taken out of the account. The third month it would have been $1,200 taken out of the account. So each month. So here's my equation. $4,800 minus 400 times the number of months has to equal $2,000. I want to know how many months it's going to take to get to $2,000. So there's my equation. Now let's create a table. So if I create a table, 1 month I would have $4,400 left. There's my balance, 3 months. So again, I'm going from the verbal to the mathematical symbolism. I'm going to a table of creating values by my input and my output, and I can see based on my table that in 7 months I would have, after 7 months, I would have only $2,000 left into my account. So again, looking at and analyzing it through a table. Here's my graph. Starting out with $4,800, looking at, here is my graph in 7 months, and I'm showing that it is a constant decrease. Why? Because every month I'm taking out $400 from my account. But this is a decrease and not an increase. I'm taking out $400. So here I have a line that's not increasing. Here I have a line that is decreasing at a rate of $400. So it's for every month, my balance is going to decrease by $400. So the ratio here is 400 to 1.
And as the teacher, you have the decision to make in terms of pedagogical decisions. How are you going to start with this problem? Are you going to start by trying to show them how the equation works? Are you going to start with a table of values? Are you going to start with trying to get them to draw the graph? That's your decision. What we're saying to you is no matter which decision you make or where you wish to start this, the students have to see the other two, because that's what the whole business is with the numerical, the graphic, and the algebraic. And those are the three aspects of the algebra that we have to get across to kids, that there's a numerical aspect that develops the generalization, there's a graphical aspect that gives them the visual, and finally there's the algebraic aspect that gives them the more general. And you as the teacher have to decide which is the way to go with this. In terms of equations, then, what we'd like to do is move on to how that type of thinking can talk to students about how to solve equations. And the first thing we'd like to do is talk about not so much solving equations, but building equations. And we call this constructing equations. And what we'd like to do is show you some videos now of the M4 model, the kinesthetic, the language, the connecting to symbolism, and symbolism, of how you would get students, to develop their equations.
Years ago, Frank DeManna and Bert Waits, who are big in higher education, and when dealing with when graphing calculators came out and how people were worried how graphing calculators would change everything, they talked about a rule of three. And they stated that the rule of three was doing things numerically, graphically, and algebraically. Then as time went on, they started to talk about the rule of four. The rule of four was graphically, numerically, algebraically, and communication. Being able to state that, okay, I can do things numerically. I could have started this problem with a table. I didn't have to go right to the algebraic. I could have did it with a table, saying that, okay, after 1 month I would have this, after 2 months I would have this, after 3 months, graphing it, and then stating, okay, now let's do it for general. How many months before I have no money? So therefore, looking at this and stating that I can go from the numerical to the graphical to the algebraic, now looking at how do I communicate this? So it's called the rule of four. And that was, I remember when Bert Waits and Frank DeManna started to develop their textbooks and we were looking at them and working with them, that kind of stuck in my mind, because that's not all new too. That goes back to the principles based on NCTM, being able to take them through the stages, looking at what level our students are, what are their habits of mind, how do we get them from point A to point B to point C. Again, looking at developing these skills, these critical thinking, being able to analyze. So now let's look at our videos.
Okay. And in this first video, what we want you to think about is that an equation is, in a sense, a theorem. It starts with the term if. It is not a matter of just being there. So in this first equation, we're going to have something called A, and that's going to equal, I believe, 2, if my memory is correct. And the question is, if A equals 2, everything else follows from that. So let's take a look.
Yeah, it's fine.
We're going to talk about a balance scale and how we can balance things in algebra. Now here I have a balance scale, and on the left-hand side, I am going to balance 2 1s. And on the right-hand side of the balance, I'm going to balance that with an A. And I'm going to assume that 2 1s balances 1A. Now, I can add anything I want to each side of the balance as long as I add the same thing to each side of the balance. So what I'm going to do on the left-hand side is I'm going to add 2 A's. But that means that I have to add 2 A's to the right-hand side of the balance. Now I've added the same thing to both sides of the balance, 2 A's, and that gives me 2 A's and 2 1s balancing 3 A's. I'm now going to add some 1s to both sides of the balance. On the right-hand side, I'm going to add 3 1s, which means then I have to add 3 1s to the left-hand side. So now my balance reads 2A and 5 ones balancing 3 A's and 3 ones. And that's because we started with the balance that said 2 ones balances 1A. In the next one, what we're going to do is we're going to link what we did with some words that we normally just say to children and students and write symbols. In this case, what we're going to do is we're going to use the words themselves. We're going to construct a balance again, and this time we are going to write it out using symbols. The result of that is that on the left-hand side, we have 2A plus 2 balancing on the right-hand side 3A's. Now, as we did before, we are going to add 3 ones to the right-hand side and 3 ones to the left-hand side. And we record that. Add 3 to both sides. And what we get when we do that is, on the left-hand side, we get 2 A's and 5 ones balancing 3 A's and 3 ones. And let's record that. So on the left-hand side of the balance, we have 2 A's plus 5 ones balancing 3 A's and 3 ones. So our final balance is 2A and plus 5, or 2A and 5 ones balancing 3 A's and 3 ones. What we've written here, 2A plus 5 balancing 3A plus 3. And the reason we have this balance is because we started with the original balance of 2 ones balancing an A, which we wrote up here, 2 ones balancing an A. Now we go to the third point, which is the third part of the M4 model, which is actually connecting everything that we've done to the symbolic structure or the symbolic representation that we want children and students to bring to the mathematics. In our last video, we started with a balance. And we're going to do the same thing this time, except what we're going to do is we're going to write it in algebraic symbols. So let's start with the balance again. We had 2 balancing A. Now in the last video, we wrote that as 2 balances A, where we use this balance symbol to show that the 2 is actually balancing the A. In this video, we're going to write it as an algebraic equation. So instead of the balance, we're going to use the equal sign. So we have 2 equals A, and that's where we start. Now, going back to our last video, the first thing we did after we had the balance, or now that we have the equation, was we added 2 A's to each side. And we do that again. So we add 2 A's to each side. Now we show that as adding 2A to the left side and adding 2A to the right side. When we do that, if we look at our chart, we have 2A plus 2 balancing or equaling 3A. So we have 2A plus 2 equal to 3A. The next thing we did in our last video was we added 3 to each side. So let's add 3 to the left side and 3 to the right side. And let's record that. So we added 3 to the left side and we added 3 to the right side. On the left side of our balance, we now have 2A and 5, or 2A plus 5, and on the right side we have 3A plus 3. So now we go to our equation and we record that. We have 2A plus 5 is equal to 3A plus 3. So now from our balance, 2 equals A, we wrote the equation 2 equals A. And from all of that, we now have the balance 2A plus 5 balancing 3A plus 3, or the equation 2A plus 5 equals 3A plus 3. And finally, we go to the symbolic level. Again, what we're doing at the symbolic level is bringing to bear the language and the knowledge that the children have from working through the kinesthetic and the linking to the language. Now we do the symbolic. What we're going to do now is we're going to start with the equation 2 equals A. And we're going to construct an equation from that. So the first thing we're going to do is we're going to add 2 A's to each side of the equation. Now remember, as with balances, when you're dealing with equations, you have to add the same thing to both sides to keep the equality. The result of that is I add 2 A's and 2, and I get 2A plus 2. On the right-hand side, I have 1A. I add 2 more A's, and that gives me 3A. And since we added the same thing to both sides, it remains equal. The next thing we are going to do is we are going to add 3 to both sides. So on the right-hand side, I'm going to add 3. And on the left-hand side, I'm going to add 3. And the result of that is, on the left-hand side, I have 2 A's and 2 1's. Adding 3 more 1's gives me 2 A's and 5 1's, or 2A plus 5, equaling, on the right-hand side, 3A plus 3. So, what we have done is, from the equation 2 equals A, by adding to both sides certain things, we've constructed the equation 2A plus 5 equals 3A plus 3. Now, we call this deconstructing equations because we constructed equations. But in actuality, what we're going to be talking about now is solving equations. And so, again, we start with tiles. What we're going to do in this case is we're going to set up an equation and figure out what the variable will equal. Remember now, the way we start off is the first one is always an if statement. If we have this equation, then we are eventually going to get a variable that has a certain value. So let's take a look at how we would do solving equations or deconstructing equations using tiles.
In the previous videos, we showed you that basically adding to both sides keeps the balance. So that's getting the students to understand that what I do to the left side of an equation, I have to do to the right side because it's a balance. So I think building equations starts them with the process of knowing that if I subtract from one side, I have to subtract from the other. If I add to both sides, I have to add to both sides. If I divide, I have to divide both sides. So it's getting them into the habit, again, the habit of the mind of seeing a repeated process here, an algebraic strategy. So once they learn that you have to keep the balance, and I tell my students it's like sitting on a teeter-totter, that you have to continue keeping the distance the same because you need it balanced. Well, what happens now after I've created this equation? I want to solve the equation, and that's what the mathematical problem solving is all about. How do I create an equation? Making sure it's balanced on both sides based on the terminology. And now how do I solve it? By deconstructing it. So this is the important part of how we do our problem solving. So let's look at what we have here.
Let's start with the balance of 2 A's and 5 1's balancing 3 A's and 3 1's. And what we want to do is we want to find out what would balance 1A. And this is the way we could proceed. First of all, on each side of the balance, we have A's. We have 2 A's on the left side, we have 3 A's on the right side of the balance. So let's take away 2 A's on the left side, but in order to keep the balance, we must take away 2 A's on the right side. So now our balance becomes 5 is balancing A and 3 1's. Remember, our goal is to get A on one side of the balance by itself. Right now we have A and 3 1's balancing 5 1's. So let's take away these 3 1's. We now have A by itself. But in order to keep the balance, we must also take 3 1's off of the left side. And when we do that, we've accomplished what we wanted to do. Namely, we now have A by itself on one side of the balance, and we're seeing that A balances 2. So, when I have the balance 2A and 5 balancing 3A and 3, that means that A will then balance 2. Now we move on to how we take this idea and start to apply symbolism to it, but using the words that we say to children or students as we do these equations. Here we have our balance again. We have 2A and 5 balancing 3A and 2. And this time what we're going to do is we're going to record our balance. So on the left side of the balance, we have 2A and 5 balancing 3A and 3. Now remember, our goal is to get A on one side of the balance alone, balancing numbers on the other side. The first thing we did was we took away 2 A's. So let's record that. Take away 2a from both sides. And remember, we have to take it from both sides in order to keep the balance. When we do that, we now have on the left-hand side 5, and that is balancing on the right-hand side a and 3. Now, we want to get a alone on the right-hand side. So what we can do is we can take away 3 from the right-hand side. But in order to keep the balance, we must also take 3 away from the left-hand side. And let's record that. So we take away 3 from both sides. When we do that, we now have on the left-hand side of the balance 2, and on the right-hand side of the balance a. So we record that as 2 balances a. And now we've accomplished what we wanted to do. We now have a value of a, namely that a balances 2. To review, what we did was we started with the balance 2a and 5 ones was balancing 3 a's and 3 ones. And when that occurs, then we know from our work that a will balance 2 ones, and that is what we've recorded here, that 2 balances a, or a balances 2.
The third part of the M4 model is actually showing, using the tiles and the symbolism, how they work together and how one links to the other before we set on our course of just using the symbolism.
We have our balance here again, 2 a's and 5 ones, balancing 3 a's and 3 ones. Now in the last video, when we did that, we recorded it using balance symbols. In this video, we are going to record it using algebraic symbols. So the left-hand side is going to be 2a plus 5. The right-hand side is going to be 3a plus 3. And instead of using the balance symbol, we are going to use the equal sign. So the balance, 2a and 5, balancing 3a and 3, forms the equation 2a plus 5 equals 3a plus 3. Now, again, our goal is to get 1a on a side of the balance. Well, on this balance side, we have 2 a's. Here we have 3 a's. Let's take 2 a's away from the left-hand side and 2 a's away from the right-hand side. When we record that, we say that we subtract 2 a's from each side. And let's see what we have left. On the left-hand side, we're going to have 5 ones. On the right-hand side, we're going to have a and 3 ones. So when we record that, we have 5 equals 1a plus 3. We now have 5 on the left-hand side and a and 3 ones on the right-hand side. Our goal is to get a by itself on one side of the balance. On the right side of the balance, we have a and 3 ones. So let's take away 3 ones from the right-hand side of the balance. That means we must take away 3 ones from the left-hand side of the balance. And let's record that. So on the right-hand side, we're going to take away 3, and on the left-hand side, we're going to take away 3. And the result of that, on the left-hand side, we're going to have 2, and 5 minus 3 is 2,
And on the right-hand side, we're just going to have A, because 3 minus 3 is 0. So when we start with the balance 2A and 5, balancing 3A's and 3, we end up with 2 balancing 1A. That means that the equation 2A plus 5 equaling 3A plus 3 is solved when 2 equals A.
The next obvious step then would be to take what we've done up to this point and just do it with symbols. So what we would do is we would start off with the equation. But remember, that equation says if we have these symbols equaling these symbols, then 2 is equal to A. So remember that an equation is always, in a sense, a theorem. It's an assumption that we're starting with two ideas equal to each other, and that will give us an answer at the bottom where one of the variables, one variable, is equal to a quantity.
Okay, now let's see how we can tie this all together. So we're going to skip this video. And here is a problem. Right. Now this is a problem that can be done in middle school. It can be done in Algebra 1. It can be done in calculus. It can be done in pre-calculus. This is a very standard problem that you can do at various levels using different techniques and approaches. So here's the problem. Mrs. Brown's class will raise rabbits for their spring science fair. They have 24 feet of fencing, which to build a rectangular rabbit pen in which to keep the rabbits. Mrs. Brown students want their rabbits to have as much room as possible. How long would each side of the pen have to be so that they could have the sides of the pen if they only had 16, oh, that's the changing, different scenarios. So you're starting out with 24 feet of fencing. They want them to have the maximum number of area so that they could be in this pen. So how would I determine this? What approaches would I look for? So let's think about how you would do this. So let's look at the approaches for this problem. How would I approach this problem? Okay. I can approach this problem by building pens with physical models, my manipulatives. Draw the pens on grid paper. Make a table of the dimensions of possible pens. Make a graph. Set up an algebraic equation. Okay. I've done this problem similar to this problem with 3rd and 4th grade students. I gave them a piece of string 24 inches long, saying that the inches would represent our feet because I'm not going to give them 24 feet of fencing. So giving them a piece of string 2 feet long and asking them to manipulate this string, and in manipulating this string, come up with different rectangles that they could, and looking at and recording it. And I also gave them Cheez-Its to do this problem. A Cheez-It is a 1x1, and I didn't give them the tiles because after they're playing, you'd like to feed them, and I know that sometimes in the schools today you cannot do that. So giving them this and looking at which pen had the most Cheez-Its, so it would be the greatest area. So looking at basically giving them manipulatives to start this. This is in the 3rd and 4th grade. You can take this and do the same thing in middle school, but now you're going to take it to a different dimension. Maybe you don't want to give them the string in middle school and in high school. You want them to draw these pens on a grid. But I think students like manipulating the string and talking about it. So these are the approaches you can use to do this problem. So let's look. Here, you could give them tiles to do this or rods to do this, making sure that they have the rods or the sticks to make a pen, and then manipulating this, where I say that each one of these sticks or rods is a foot, and you give them 24 of them, and so now manipulating it to draw, to build a fence. So I'm building this fence. So this is another way. I gave the students string. You can give them rods. You can give them string. So they're building a fence. They're building a mathematical model here, a model. I gave them Cheez-Its. You can give them the tiles. So I'm giving them the tiles, and they're placing the tiles inside the pen as the size of the pen is changing. As I'm changing the length and the width, how am I changing my area? So again, it's now they're looking at this, and as they're doing this, they can be recording this. So they're actually manipulating it. They're now recording it. So I have a recording device so that I could look at this and analyze it. And again, it takes it to all different levels. In the 3rd and 4th grade and even middle school, after I look at my table, I can look at the table and come up with some conclusion. So you're looking at this and they're manipulating it. They're having a lot of fun, especially if you give them the Cheez-Its, because all they want to do is eat them. So here's a table. Here's my table. Here's my length. Here's my width. I talk about the perimeter is constant. The perimeter is always 24. The perimeters. And what would my area be? Now my area in the 3rd and 4th grade, they can find it, since they may not know an area formula at this point. They can count the number of tiles or count the number of Cheez-Its that I had inside my rectangle. And they look at this, and as they're looking at this, they can see that after I get to 6, of my length is 6 and my width is 6, I start to get, I had 5 and 7, now I have 7 and 5. So therefore, basically my numbers are going to start to repeat, and I'm going to get the same number, except that my rectangle is now on its side. So if you're looking at this, a 3rd and 4th grader could analyze this just by looking at the table. Let's look at this table. So it's a structure that's getting them ready to think about an abstraction. How do I get this? And I can look at this and say, well, it looks like it was increasing. It hit 36, and now it's going to start to decrease. So what does that mean? My length and width would have to be a 6 by 6. So here's a problem that you can do in elementary and middle school by looking at them, analyzing a table. Analyzing a table. Here, I can get middle school and high school students to create a graph. And the way I want to create this graph is I want to create the length and area. Area is a function of my length. So if I look at this, as I'm looking at this, area is a function of my length. So what do I notice about this graph? This graph is not linear. This graph is not a linear graph. And in algebra today, they're looking at, when you're doing with the Common Core, that we do not live in a linear model. We do not live in a linear world. So I now have a graph that's not linear. It shows me that it is increasing. It increases, it hits a point, and then it starts to decrease. But ask the students to describe this graph as if, what is the difference between this graph and the graphs that I have shown you before? This is not increasing at a what? This is not increasing at a constant rate. This is not linear. Having them be able to make that distinction that my ratio here is not constant. I do not have slope here because slope is a constant rate of change. So I'm looking at this graph and I'm making an interpretation about how my numbers or my area is increasing and what happens as I change my length. I have an input, I have an output. Input, output is not just linear. It could be any type of relationship here. So here I'm looking at my graph. So as I stated, what are my approaches? I can use a physical model. I can use a table. I can use a graph. So now I have my graph. What's my interpretation? So if I look at this graph, and I say, oh, it looks like that when the length is 6. So if I go back to what is my perimeter is constant and I have 24 feet of fencing. If my length is 6, what would be my width? So that would take it to the next approach of here is an equation and here is a graph. Here is my perimeter model. Here is my area model. And here is my graph. So what you're looking at here is taking a problem and looking at an approach, going from the very simplistic with a physical model to the abstraction, which is my algebraic model, and looking at my graph. So here is my graph, here is my algebraic model. The problem then is asking, I started out with 24 feet of fencing, what would happen if I had only 16 feet of fencing? So again, looking at this and going through the same stages, and then asking the students if they see a relationship between when I had 24 feet of fencing and when I had 16 feet of fencing. Could I make a conclusion about what my pen would look like? What would it look like? So when you're looking at this, what conclusion could they possibly make? And eventually they're going to say that the maximum area occurs when I have a square. So again, it's looking at what is the structure here, looking for a pattern, looking for precision, making a mathematical model, making an interpretation. So you're taking the algebraic structure of how to solve an equation, how to build a mathematical model, and then taking it and applying it to a problem, a word problem, where they're going to use all of their tools, and that's exactly what the Common Core is stating. Take the tools and use the tools properly. So I can use my models, my manipulatives, my table, my graphs, and my algebraic equations to be able to come up with a solution. So you're looking at all of the algebraic structure, not just graphing points, not just solving equations, but putting it all together, looking at equations and graphs to come up with a solution to a problem. So I hope that we have given you something to think about this afternoon, looking at algebra not just from solving equations, but how I construct equations, how I deconstruct equations, how I look at slope as a constant rate of change, looking at a different way of introducing that rate of change, and then finally taking all of my tools and solving a problem and having the students realize that we do not live in a linear world and not everything comes out to be a linear equation. Because if you go back and you look at what the Common Core is doing, they're introducing exponential models or exponential graphs. They're introducing quadratic graphs. And they're not asking the students to solve those exponential graphs, but to analyze and interpret them. And I think that's the important part. What is the analysis and interpretation? Can I communicate with what my graphs are telling me, or what are they conveying to me? Can I communicate? Can I describe that to someone who may not understand it? Can I describe it? So, as I stated, I hope that we've given you something that you can think about and something that you can use in your classroom. So are there any questions or comments? You can use the chat for any question or comment that you might have. No questions?
Just not.
So if there are no questions, or comments, I thank you for participating this afternoon. And as I stated, I hope that Frank and I have given you something to think about. And if you have any questions or comments and you would like to contact us, here's Frank's email and my email. Please feel free to email us any questions or comments. We'd love to hear from you. So thank you for participating this afternoon. I hope that we've given you something to think about. Thank you.